Jai Hind to all. This is Ritika Dhyani from Akgec. I have been working here as an assistant professor, and today's video lecture is on the topic deadlock. First of all, let's learn about what is a deadlock. See, each and every process needs some resources to complete its execution. However, the resources is granted in a sequential order. Deadlock arises when one process requests for some resource and that particular resource is already acquired by some other process, and similarly this goes around and it forms a circular cycle which results in deadlock. So firstly the process requests for some resources, OS grant the resource if it is available, otherwise the process waits. The process uses it and release on the completion. This is the simpler sequence in which a process or a task is being performed in operating system. But when the process requiring some resource, that particular resource is already acquired by some other process and it is not available for the next process, then what the process will do, it will wait for some time, and that if this happens in a circular fashion, that one process is waiting for some resource that is acquired by some other process and that particular process is also waiting for some other resource, then this will arise the situation of deadlock. So let's see here, a deadlock is a situation where each of the computer process waits for a resource which is being assigned to some another process. In this situation, none of the process gets executed since the resource it needs is held by some other process which is also waiting for some other resources to be released. Let's see here, we are having three processes here, and this arrow shows that this particular resource is acquired by process P1. Similarly, R2 is acquired by P2 and R3 is acquired by P3. Here we can see, apart from acquiring this particular resource R1, P1 also requires R2 for its execution, and till that time, till the P1 does not get the R2, it cannot complete its execution. So this process will not execute further, hence results in waiting state. Similarly, in the same fashion, P2 is acquiring R2, but it also is waiting for R3 resource, and this happens in a circular fashion. So no process is getting executed at this particular time. This results in deadlock. So there are basically four necessary conditions for deadlock, and each of the condition must be happening at the same time or simultaneously. So the first condition is mutual exclusion. A resource can only be shared in a mutual exclusive manner. It implies if two processes cannot use the same resource at the same time. See, what does it mean? It means that if, let's say, R2 is shareable, let's make this shareable resource. If this particular resource is shareable, then it can be used for P1 process as well as acquired by P2 because it is shareable. But because mutual exclusion says that no resource can be used by the two different processes at the same time, so it is not shareable, hence the deadlock happens. So this is the first necessary condition for the deadlock to be happening. Next is hold and wait. Hold and wait, as the name suggests, one process is holding a resource and also waiting for some other resource. This is what this condition says. So as we can see here, P1 is holding R1 and waiting for R2. So we can see here that this particular process or all these processes are also in hold state as well as in waiting state. If this happens at a time along with all the three other necessary conditions, then the system is definitely in deadlock. Third one is no preemption. The process which once scheduled will be executed till the completion. No other process can be scheduled by the scheduler meantime. It means if here let's say P1 gets preempted. Preempted means if we are able to stop the P1 process in between, so when this particular process stops, this will release this R1. So this R1 becomes free, which is required by P3 process, as P3 is holding R3 and it is waiting for R1, which is now available. So P3 can execute. When P3 can execute, it will release R3 as well and R1, which the P3 is holding. When P2 learns about that R3 is available, then the completion of this process also gets in terms, and after that, after releasing R2, P1 gets the P1 gets the R2. So here we can see that if all these three processes can be preempted at different times, then the situation of deadlock is not happening. But for the for this necessary condition to be true, any of the process cannot be preempted in between before its completion, right? Moving on to the next necessary condition, which is circular wait. Here we can see it is forming a circular cycle. One process is holding some resource, requiring some other resource as well. Similarly, this happening here also, and in case of P3 also. So a proper cycle is being formed here, which is a necessary condition for deadlock. All the processes must be waiting for the resources in a cyclic manner, so that the last process is waiting for the resource which is being held by the first process. So all these are the four necessary conditions, and for a system to be in deadlock, all these conditions must be happening at the same time. If we are able to, if we are able to stop any of the necessary condition, then we can say deadlock will not happen. So firstly, there are different strategies for handling deadlock. First one is deadlock ignorance. It is the most widely used mechanism. In this approach, the operating system assumes that deadlock never occurs. It can never occur. It simply ignores the deadlock. This approach is best suitable for single end users, because as a user, sometimes our system got stuck and we just restart the system for our normal execution. So this is the simplest way of handling the deadlock. In these type of systems, the user has to simply restart the computer in case of deadlock. Second way to handle deadlock is to prevent the deadlock. Deadlock happens only when mutual exclusion, hold and wait, no preemption and circular wait holds simultaneously. If it is possible to violate any one of the four conditions that is happening at the same time in a particular system, then deadlock can never occur in the system. The idea behind this approach is very simple, that we have to fail any one of the necessary condition to prevent the deadlock. For deadlock prevention, let's start with, are we able to stop or violate mutual exclusion? See, mutual exclusion from the resource point of view is the fact that a resource can never be used by more than one process simultaneously. But if a resource could have been used by more than one process at the same time, then the process would never have been waiting for any of the resource. the main problem here is that we cannot force a resource to be used by more than one process at the same time, since this is not practically feasible to make any of the resource shareable anytime. So we are not able to violate or stop or prevent the mutual exclusion to be happening. So there is no chance that we can stop this particular necessary condition. Now let's learn about hold and wait, if we are able to stop it or not. Deadlock occurs because there can be more than one process which are holding one resource and waiting for some other resource in a cyclic order. A process must be assigned all the necessary resources before the execution start. A process must not wait for any resource once the execution has been started. It means, let's say we are having P1, P2 resources, processes, and let's say two resources there are, and these two resources are acquired by R1 is acquired by P1 and R2 is acquired by P2. P1 requires R2 and P2 is waiting for R1. So here we can see a hold and wait situation is happening and in a cyclic order. If we are able to provide all the resources that P1 needs for its completion before its execution, then we can stop this particular necessary condition, because if we are able to provide P1, R1 as well as R2 before its execution start, then P1 will be getting both of the resources and it gets completed. It releases both of the resources and these two resources will now be available for P2 process. But this can be implemented practically if a process declares all the resources initially. However, this sounds very practical but can't be done in computer system, because a process can't determine all the necessary resources initially. Some resources may be needed in between. So let's have a look on if we can stop this particular necessary condition, which is no preemption. A deadlock arises due to the fact that a process can't be stopped once it starts. It gets after it gets completed, it can be terminated from the system. However, if we take the resource away from the process which is causing deadlock, then we can prevent the deadlock, of course, but it is not a good approach or practically feasible, because if we take a resource away which is being used by a process, then all the work which is already done by that particular process using that resource can become inconsistent, or the whole system will go in inconsistent state. So we cannot prevent this particular necessary condition to be happening. Next one is circular wait. We can practically avoid circular wait. We can assign a priority number to each of the resources. A process can't request for a lesser priority resource. This ensures that not a single process can request a resource which is being utilized by some other process, and so that no cycle will be formed. So only this condition is there that we can avoid or we can prevent to be happening to stop the deadlock. Third strategy for handling a deadlock is deadlock avoidance. In deadlock avoidance, operating system checks whether the system is in safe state or in unsafe state at every step which the operating system performs. The process continues until the system is in safe state. Once the system moves to unsafe, the OS has to backtrack one step. In simple words, the OS reviews each allocation so that the allocation doesn't cause the deadlock in the system. Let's see it in detail. So the first way to handle this particular deadlock is using the resource allocation graph. What this graph says, that we need to denote all the processes using circle and resources using square. or rectangle. Here this circle denotes that only one instance is possible, or only a one particular process can use this resource, right? So here let's consider three processes, P1, P2, P3, and two type of resources, R1 and R2. As we can see in this example, the resources are having one instance each, because here only one circle is drawn, which is this particular resource can be used by P1 only, or one process only. So now using RAG we can identify whether this particular system is in deadlock or not. Let's see, P1 is holding R1, and at the same time P1 does not require any of the other resources for its execution. So once P1 gets completed, it gets terminated and release R1. So now R1 is, this process already gets terminated, completes it. Now R1 is available for these two processes. Here we can see, firstly, when P3 is waiting for R2 and R1, P2 is acquiring R2, and we can assign this R1 to P2 first. This process also gets completed and terminated as well. Now what happens is, P3 after its termination, it will release both of these resources. Now P3 will use these three resources and the whole system is in safe state. We can identify this if the system is in safe state or not by simple seeing one thing, that if any circular or cycle is forming there. As we can see, there is no cycle, so we can say that this system is not in deadlock. Now let's see in this example. Here we are having three processes and three resources. Each resource is also having one instance. That means it can be used by one process at a time. Next, only checks for a cycle. Yes, let's see here. Firstly, let's start from this P1, this, as we go here, and now back to P1. So yes, a cycle is formed here. So we can say that this particular, without any doubt, this particular system is in unsafe state and deadlock may occur in this system. So that is how RAG is used, or resource allocation graph is used. Next one is for the only deadlock avoidance, RAG as well as Banker's algorithm can be used. It is a resource allocation and deadlock avoidance algorithm that tests for safety by simulating the allocation for the predefined maximum possible amounts of all the resources, then makes an S-state check to test for possible activities before deciding whether the allocation should be allowed or continue. Basically, let's see an example, then you will learn about it more clearly. Here we can see we are having 5 processes, and these ABC are the different resources, and the value representing here is saying that P0 is holding none of resource A type. Allocation is representing these resources are allocated to, these many resources are allocated to these processes. Maximum is showing that this process needs maximum of 7 resources of type A, 5 of type B and 3 of type C. So that is how this table shows. And lastly, available shows that after allocating these many resources from the total resources, these resources are now available. 3 resources of type A, 3 resources of type B and 2 resources of type C. So now let's see, another next step is here is to make need matrix. Need matrix will show that how many more resources P0 requires for its execution. So that's how need matrix is formed. So let's see here. Need matrix, how we are going to fill these values? We need to subtract allocation from max. Simple. That's how a need matrix is formed. So for A, it is 7 minus 0, 7, 5 minus 1, 4, 3 minus 0, 3. Next, 3 minus 2, 1, and similarly 2, 2. Next, 9 minus 3, 6, 0, 0. Next is 2 minus 2, this 2 minus this, 0, 2 minus 1, 1, 1, 4 minus 0, 4, 3 and 1. This is how we form need matrix. Moving on to the next step, which is, so here need matrix is already there, which we already calculated in the previous slide. This is showing the total number of resources of each type. Let's start with the safety algorithm. Whether this after allocating these many resources to all these processes, if the system is in safe state or not, if we are continuing our allocation or not. So let's start here. Firstly, we need, this is need matrix, which is the first step of the question. Next, firstly, we are going to check if the number of resources that P0 needs is available in the system or not. So we can say, we can see here that P0 needs 7 of the resources of type A. But here we are having only 3 resources available. So we are not going to process this request. Next, moving on to the P1. P1 requires A type resource, 1 only. Yes, it is available as we are having 3 A type resources available in the system. Next, B, it requires 2 only and we are having 3 resources here. Again, this request can be permitted. Next, C requires 2, P1 requires 2 resources of type C, and the system, in the system, there are 2 C type resources available. So all the need this particular process are available in the system. So we can say that we can, firstly, we are permitting P1 to execute. P1, after allocating these many resources, P1 can get executed and completed. After terminating, it releases the resources that it previously holds. So all these resources gets added up here because now these resources are also available in the system for all other processes. So here we can do, next is 3 plus 2, that is 5, 3 plus 0, 3, 2 plus 0, 2. Now the system is having these many available resources and we have even executed totally. Next, moving on to the next request, which is P2 requires 6 resources of type A. No, we are not having 6 resources available in the system. We cannot process the request of P2. Next, can we process the request of P3? Yes, as we can see here, it requires none of A type resource, only one B type resource, which is 3 available in the system, and one of C type resource, which is also 2 available in the system. So yes, we can next perform process 3. It gets completed, it releases these many resources, and now these resources are also available in the system. So now the system is having these many resources: 7, 3 plus 1, 4, 2 plus 1, 3. Now we are having these many resources available. Next, after these two processes are already done, next we check for P4. It is up to you whether you want to check for P4 or you want to check for P0. As you can see, now available resources are also same as P0 requires. So we can perform P0 also or P4 or any of the resource. It is up to you. The sequence is up to you. Next is P4. P4 requires 4, 3, 1. 4, 3, 1. 4, 3, 1. Obviously, this value is lesser than the available resources. So P4 gets executed here, and all the resources are now available in the system, which becomes 7, 4, and 3 plus 2 is 5. So this P4 gets completed. Next, again going back to P0, 7, 4, 3, 7, 4, 5. Obviously this value is larger, so P0 also gets completed and releases these resources. So this will become 7, 5, 5. After this, we are only having P2. Let's check if the system can process this request or not. It requires only 6 resources of type A, and we are having maximum of 7 resources available in the system. So yes, we can perform this particular request also. So after giving these many resources to this particular process, this process gets executed, terminated, and it releases its allocated resources. Now the system will be having 10, 5 plus 0, 5, and 7 plus 5 plus 2, 7. These many resources after the execution of all the processes. So this is the safe sequence. This represents safe sequence. This safe sequence must not be unique, as I already told that after P4 you can go to P0, or you can it's up to you whether you want to run P2 process. So this needs not to be unique, but it shows if this particular sequence is present, then this shows that deadlock is not there if we are providing these many resources to these processes in the particular sequence. Also, you need to check after the execution, this value must be equals to the total resources available in the system. So this is how Banker's algorithm works. Next strategy for handling deadlock is detection and recovery. This approach let the process fall in deadlock and then periodically check whether the deadlock occur in the system or not. If it occurs, then it applies some of the recovery method to the system to get rid of the deadlock. So in this particular step where the system falls in deadlock and it checks whether there is deadlock in the system or not, we already studied about RAG, which is used for single instance. In case of multiple instance, we are having Banker's algorithm, which we already studied. So this is how deadlock detection is happening in the system. If we can detect the deadlock, in case of single instance we use RAG, resource allocation graph. In case of multiple instance resources, we use Banker's algorithm. Next one is recovery. Now we are having two main things, which is One is resources and the other one is process. For resource to be recovered, either we need to preempt any resource, or next one is we need to roll back that resource to a safe state where the deadlock is not happening. That is how a particular resource is recovered. In case of process, we can perform two things. Either, let's say we are having P1, P2 and P3, R1, R2, R3. These are processes and these are resources. Same way, using RAG, we can say that there is cycle, and we can detect that deadlock is already there. To recover this execution of P3, then what will happen? It will release R3 as well. R3 is now available. R3 is available, which is required by P2. If P2 is getting R2 as well as R3, its execution gets completed. Next, we have this after execution of after termination of P2, it will release R2, which will be given to P1, and now P1 also gets completed. So this is how our deadlock is recovered, by only preempting one of the process. So this is one of the solution. Second solution is, if the system is in deadlock, we already detected that there is deadlock, then what we can perform is we terminate all the processes at the same time, so that the deadlock gets terminated from the system. That is how recovery happens. Thank you.